All right, welcome back to AI by AI. We hear constantly about these massive world-changing models. But what happens when you take them out of the lab and into the real world? What happens when you need an AI to understand a messy database, or when your data is corrupted, or when you don't have a supercomputer to run it on?
Exactly. That's where the real innovation is happening right now, and it's the theme for today's episode, making AI smarter and more efficient for the real world. First up, we're looking at how to get large language models to actually reason over a structured database. Right now, we basically just flatten it all into text, which is a total mess. We'll break down a new paper that uses graphs to teach LLMs the relationships in the data. Horror.
And speaking of messes, what if your data isn't just structured poorly, but is actively noisy or even corrupted? We've got a fascinating paper that explores whether certain types of problems are still learnable. It gets into a concept called sample compressibility, which is just a fancy way of saying a problem can be learned from a small core set of examples, and shows how we can make learning robust even when the data is bad.
Sticking with complex data, we're then diving into the world of graphs. Graph neural networks are great, but they can be easily fooled by two different graphs that look similar on the surface. We're going to talk about a new technique called SpectRe that gives the AI a kind of topological X-ray vision. It uses something called persistent homology, basically a method for tracking features like loops and holes, to create a much richer understanding of a graph's true shape.
I love that. And we're going to see how these advanced techniques apply to a critical area, healthcare. First, can the sound of your voice be a biomarker for cognitive impairment? A new study tested existing AI models on this, and the results are fascinating, especially the finding that how you speak, your tone, your rhythm was a much better predictor than the actual words you used.
And we're closing out with another healthcare application that tackles the efficiency problem head-on. How do you train a powerful medical diagnostic model with a warehouse full of GPUs? We'll look at a framework that uses reinforcement learning, basically rewarding the AI for good reasoning, to teach a small model not just to be accurate, but to explain its thinking like a doctor would, all while training on a single GPU.
So we've got smarter database queries, robust learning, next-gen graph intelligence, and two huge looks at the future of AI in medicine. It's a packed show. Let's jump in. So we're diving into this paper, Large Language Models Are Good Relational Learners, and it tackles a really fundamental problem. We know LLMs are amazing with text, but what happens when you try to point them at a relational database? You know, the kind of structured data that runs most of the world's businesses.
Right? It's a huge disconnect. The typical approach is to just flatten the database into a giant text file, a process called serialization. But the paper points out this is a terrible solution. You lose all the rich structural information, the links between tables, the primary and foreign keys. It's like taking a complex 3D model and squashing it into a 2D drawing.
Exactly. And not only do you lose the structure, but you create massive redundancy. The same piece of information might get repeated over and over. Plus, these text files can get so long they exceed the context window of even the biggest LLMs. So the authors here propose a new architecture to solve this called Rel-LLM.
Rel-LLM. So Rel for relational, I assume. What's the core idea? How does it avoid just turning everything into a flat text file?
Instead of flattening the data, it embraces the structure. It uses a graph neural network, or GNN, as a kind of translator. First, it represents the entire relational database as a massive graph, where each row in a table is a node, and the key relationships between tables are the edges connecting them.
Okay, so it's thinking of the database as a network. That makes sense. What does the GNN do with this graph?
The GNN acts as an encoder. For any given task, like predicting customer churn, it doesn't look at the whole massive graph. It intelligently samples a relevant local subgraph around the customer you're interested in. Crucially, it does this with temporal-aware sampling, meaning it only looks at data from before the prediction time to avoid cheating by looking into the future.
That's a critical detail. So the GNN processes this small time-aware subgraph, and then what? Does it output text?
No, and this is the clever part. It outputs a set of embeddings, basically compact numerical representations of the nodes in that subgraph. These embeddings are what they call a structured relational prompt, or a graph prompt. This prompt is then fed to the LLM.
So it's not feeding the LLM raw text from the database, it's feeding it these condensed, structure-aware numerical vectors from the GNN. How does the LLM even understand those?
Through a technique called graph prompt tuning. The GNN's output embeddings are passed through a small projection layer that maps them into the LLM's own internal language, its latent space. This acts as a soft prompt that guides the LLM's reasoning. The best part is that the LLM itself is frozen. Only the GNN and the projection layer are trained. It's incredibly efficient.
That is efficient. It's like teaching a GNN to speak the LLM's internal language. The paper also mentions a pre-training phase. Why is that necessary?
The pre-training is what makes the model so good, especially in zero-shot scenarios. They use a self-supervised task called masked attribute prediction. They take a subgraph, hide the features of a specific entity, like a customer's purchase history, and then ask the model to reconstruct those missing attributes just by looking at the surrounding graph structure.
Ah, so it forces the GNN to learn how to encode meaningful structural and relational information into its embeddings. If it can reconstruct the data, it must understand the relationships. That probably explains its strong performance.
It really does. Looking at the results in Table 1 for entity classification tasks, Rel-LLM consistently outperforms baselines. It beats traditional models like LightGBM, but more importantly, it beats other LLM-based methods like ICL, which is that standard approach of feeding in text-based examples.
And the paper makes a great point about why. Those ICL, or in-context learning methods, are incredibly fragile. Their performance can swing wildly depending on which examples you show them and in what order. Figure 2 shows this clearly. ICL's performance is all over the place. Rel-LLM, by encoding the structure directly, is far more robust.
Exactly. And it's not just classification. Table 2 shows it also gets the lowest error on regression tasks, which are notoriously hard for LLMs because they involve precise numerical reasoning. This graph-based approach seems to ground the LLM in a way that text alone can't.
What I found most impressive was the zero-shot performance, which they call Rel-0. This is the model after pre-training but before any task-specific fine-tuning. Its performance is often comparable to fully supervised models like LightGBM. That's huge for real-world use where you might not have much labeled data.
It's a game changer. And they have this fascinating section on unsuccessful attempts, which is always great to see. They found that adding few-shot or even many-shot examples to the prompt didn't really help Rel-LLM. Their theory is that the model, a 1 billion parameter llama, is small enough that it's not really learning from the examples in context. The task description is enough for it to know what to do, and the graph prompt provides the necessary data.
That's a great insight. They also found that during pre-training, masking entire entities, entire rows, was much more effective than masking individual cells. Masking a cell is too easy. The LLM can just infer the value from other columns in the same row. Masking the whole entity forces it to actually learn from the broader relational structure.
Right? It has to reason about the connections to other tables to figure out the missing information. So the big takeaway here is that to get LLMs to work well with relational data, you can't just treat it like a book. You need a specialized approach that respects and preserves the data's inherent structure. Rel-LLM does this beautifully by using a GNN as a bridge, translating that structure into a format the LLM can effectively reason with. All right, let's jump into this paper on robust learnability. The core idea is about a fundamental problem in machine learning. How do you learn the underlying pattern or distribution from a set of data points? This is at the heart of everything from clustering to generative models.
Exactly. And the classic assumption is that your data is clean. But in the real world, that's almost never true. Your data might have random noise, or even worse, it could be intentionally corrupted by an adversary. This paper tackles that head-on and asks, can we still learn reliably when our data is messy?
The authors build on a really elegant concept called sample compressibility. It sounds technical, but the intuition is pretty straightforward. Can you break it down for us?
Absolutely. Sample compressibility means that for a given family of distributions, you don't need to keep your entire massive dataset to understand the underlying structure. Instead, you can compress it down to a very small representative subset of samples, plus maybe a few extra bits of information. This tiny compressed set is enough to reconstruct a good approximation of the original distribution.
The paper gives a great example with Gaussian distributions. If you're trying to learn a simple bell curve, you don't need thousands of points. In theory, you just need two specific points. One near the mean minus the standard deviation, and one near the mean plus the standard deviation. With just those two, you can get a pretty good estimate of the whole curve.
Right. The magic of sample compression is that you don't even need to know which 2 points they are. You just need to know that if you collect enough data, 2 such points are guaranteed to exist within your dataset. This existence property is what implies the distribution is learnable in a formal information theoretic sense.
So the big contribution of this work is proving that this powerful property of sample compressibility is robust. They show that families of distributions that are sample compressible from clean data remain learnable even when the data is perturbed.
And they look at 2 very different kinds of perturbation. First, there's the additive noise model. This is like random static. Every single data point is slightly nudged by some random noise, say from a Gaussian distribution. It's independent and affects everything.
The second is the adversarial corruption model, which is much more sinister. Here, an intelligent adversary gets to pick a small number of your data points and change them however they want, within some budget, specifically to fool your learning algorithm.
Let's dig into the additive noise model first. The authors find that for a compressible class to be learnable from noisy data, 2 extra conditions are needed. The first is called local Lipschitz decodability.
That sounds like a mouthful. What does it mean in simple terms?
It's a stability condition. The decoder is the function that takes the small set of compressed samples and reconstructs the distribution. This condition just says the decoder must be well behaved. If you make tiny, infinitesimal changes to the input samples, the output distribution shouldn't drastically change. It has to be smooth, at least locally.
That seems like a very reasonable requirement. An algorithm that completely changes its mind based on a tiny bit of measurement error wouldn't be very practical.
Exactly. And they show it's not just reasonable, it's necessary. They give an example of learning a Gaussian distribution where the variance can be arbitrarily close to 0. In that case, the decoder is infinitely sensitive, and they prove it's impossible to learn from noisy samples. So this stability is crucial.
What's the second condition for the noisy case?
It's called the low-frequency property. The idea here is that adding noise is like applying a low-pass filter in signal processing. It blurs out the fine details. If the true distribution has a lot of sharp, spiky, high-frequency features, the noise will completely wash them away, making them impossible to recover.
So this assumption requires that the distributions you're trying to learn don't have too much of their information packed into those high-frequency details. A significant chunk of the energy of the distribution's shape must exist in the smoother, low-frequency components that can survive the noise.
Precisely. And again, they show this is necessary. If a distribution family is all high-frequency wiggles, you can construct a sequence of distributions that look identical after adding noise, but are actually very different, making learning impossible. So, with those 2 conditions, stability and the low-frequency property, they develop a perturbation-quantization framework to prove learnability.
How does that framework work?
It's a clever 2-step process. Since you don't know the exact noise that was added to each sample, you create a grid of possible noise values. This is the quantization part. Then, for each noisy sample, you try denoising it by subtracting every possible noise value from your grid. This creates a huge set of candidate clean samples.
And because the original distribution family is sample compressible, you know that somewhere in that massive set of candidates, there's a small subset that will correctly reconstruct the distribution. The price you pay is the search, which inflates the number of samples you need to collect.
That's it. The sample complexity scales with the noise level, but it remains learnable. Now for the adversarial setting, things are different, and in a way even cooler.
Here, an adversary corrupts a small fraction S of the samples. What changes?
What's fascinating is that you no longer need the low-frequency property. Because the adversary only corrupts a few samples, most of your data is still perfectly clean. The fine details of the distribution aren't completely blurred out like they are with pervasive noise. They're still present in the uncorrupted data.
But you don't know which samples are clean and which are corrupted. How do you get around that?
With a brilliant technique that feels like something out of a detective novel. You partition your data into a bunch of disjoint groups, specifically 2S+1 groups. By the pigeonhole principle, since the adversary can only corrupt S samples in total, at least S+1 of your groups must be completely clean. A strict majority.
I see. So you run your learning algorithm on each of the 2s+1 groups independently. The S+1 clean groups will all produce very similar estimates of the true distribution. The S-corrupted groups will likely produce outlier estimates.
Exactly. The estimates from the clean groups form a clique, a cluster of results that are all very close to each other. Your final step is to simply find this large clique and pick any one of its members as your final answer. This robustly filters out the adversary's influence.
And the authors show this isn't just abstract theory. They apply these frameworks to solve two previously open problems, right?
They do. First, they tackle learning mixtures of uniform distributions. Think of approximating a shape with a bunch of rectangular blocks. They provide the first sample complexity bounds for learning these from noisy or adversarially corrupted data.
And the second one is a big one. Learning Gaussian mixture models, or GMMs, from adversarially corrupted samples. GMMs are used everywhere, so understanding their robustness is critical.
Yes, they derive explicit bounds on how many samples you need to learn a GMM, even when an adversary is tampering with your data. The sample complexity increases, as you'd expect, based on the number of corruptions S, but it shows that it's fundamentally possible.
So the overall takeaway is that sample compressibility is a remarkably powerful and robust structural property. It gives us a unified lens to understand learnability, not just in an ideal clean world, but also in the messy, perturbed reality where most data actually lives. So we know that standard graph neural networks, or GNNs, are incredibly powerful, but they have some well-known blind spots. They're great at learning from local neighborhoods, but they often struggle to capture more global structural information about a graph.
Exactly. A classic example is their inability to reliably detect or count cycles. This is a fundamental limitation tied to their expressive power, which is bounded by something called the Weisfeiler-Lemon test. To get around this, researchers have been turning to topological methods, specifically persistent homology, or pH.
Right? And for anyone new to the term, persistent homology is a really neat way to track the shape of data. For graphs, you can think of it like building the graph piece by piece according to some rule. This process is called a filtration. pH tracks when topological features like connected components or cycles are born and when they die. This gives you a summary of the graph's topology, often as a set of birth-death pairs.
But standard pH has its own limitations. It doesn't account for the features on the nodes or edges. So a method called refine was introduced to decorate these persistence diagrams with feature information, making them more expressive. The problem is, refine still fails to distinguish between some very simple graphs, especially if they don't have rich features, like if all nodes are the same color.
And that's the jumping-off point for this paper. The key idea is to enhance these persistence diagrams even further, not just with node features, but with spectral information. They introduce a new descriptor called SpectRe, which stands for spectral refin.
So what does spectral information mean here? We're talking about the eigenvalues of the graph Laplacian. The Laplacian is just a matrix you can derive from a graph that captures a lot about its connectivity. Its eigenvalues, or its spectrum, tell you things about the graph's structure.
Precisely. With SpectRe, when a topological event happens during the filtration, say two components merge and a representative vertex dies, you don't just record its birth and death time. You also compute the graph Laplacian of the newly formed component and record its non-zero eigenvalues. You do the same thing when a cycle is born.
And the results are pretty striking. The paper proves that SpectRe is strictly more expressive than both refine and just using the Laplacian spectrum on its own. They even show examples where refine fails but SpectRe succeeds, and vice versa for the Laplacian spectrum, proving they capture different, complementary information.
One of the most interesting findings, I think, is about which Laplacian to use. You might think you'd need some complex, persistent Laplacian to track spectral information through the filtration. But the paper shows something remarkable. You get all the same expressive power by just using the standard basic graph Laplacian at each step. That simplifies things immensely.
It really does. It means you don't have to venture into much more complex and computationally heavy machinery to get the benefits. Speaking of which, they also analyze the stability of these descriptors. Stability is a crucial property. It means that a small change in the input graph should only lead to a small change in the output descriptor.
And they find a fascinating trade-off. Refine is globally stable, which is the gold standard. SpectRe, because the spectrum can change abruptly, is only locally stable. This means it's stable as long as the changes to the filtration function aren't too drastic. The authors argue this is fine for most practical machine learning applications, where you're not making wild jumps in your functions.
It's a classic power versus robustness trade-off, and the power of SpectRe really shines in the experiments. On synthetic datasets designed specifically to test expressivity, like the Cayley graphs, SpectRe achieves 100% accuracy in distinguishing non-isomorphic pairs, while other methods lag far behind.
It's not just a theoretical curiosity either. On real-world graph classification tasks, integrating SpectRe with a standard GCN model boosted performance on 8 out of 9 datasets, often by a significant margin over both the base GCN and the one enhanced with Refine.
Of course, there's no free lunch. The big limitation here is computational cost. Repeatedly calculating the eigendecomposition of subgraphs can be very expensive, especially for large graphs.
True, and they acknowledge that. But they also propose practical solutions. For larger graphs, you can use approximation methods to get the most important eigenvalues, or you can use a scheduling strategy where you only compute the spectrum at, say, every third step of the filtration. Their additional experiments show that even this fast version of SpectRe retains most of its expressive power and still provides a significant boost.
So in the end, SpectRe offers a powerful principled way to inject crucial topological and spectral information into GNNs. It helps them see the kind of complex global structures they would otherwise miss, pushing the boundaries of what's possible in graph representation learning.
So we're looking at a fascinating paper today called CATCH, Cognitive Assessment Through Cookie Thief. The core idea is trying to detect cognitive impairment, or CI, using just a person's speech.
Exactly. And CI is a huge issue. The paper notes that almost 1 in 10 American adults has some form of it, but it often goes undiagnosed. Finding a simple, low-cost way to screen for it, especially in primary care, could be a game changer.
And that's where the cookie thief part comes in. This isn't a new test, right? It's a standard tool in neuropsychology.
Right. The cookie thief test, or CTT, is a picture description task. You show someone a drawing of a chaotic kitchen scene, a boy falling off a stool, a mother overflowing the sink, and you ask them to describe everything they see. The idea is to elicit spontaneous speech in a standardized way.
So the researchers here collected audio recordings of older adults doing this test. The big question they're asking is, can we take existing machine learning models, which were built for other tasks, and use them to predict CI from these recordings?
That's the crux of it. They looked at two main sources for these models. First, models designed to detect Alzheimer's disease and related dementias, or ADRD. Second, models from a field called multimodal sentiment analysis, which are usually used to figure out if someone's speech is positive or negative.
Okay, so how well did it work? Did these models translate to this new task of detecting the broader category of cognitive impairment?
The short answer is, they did, but with some really interesting caveats. The models were able to pick up a signal for CI, but their performance wasn't as high as in their original tasks. For example, one of the best-performing models from a study by Ying et al. Achieved a performance metric called AUC of 0.672. For context, a random guess is 0.5, and a perfect classifier is 1.0. So it's definitely better than chance, but not ready for clinical prime time just yet.
That makes sense. CI is a broader condition than Alzheimer's, so the signs might be more subtle. But the really interesting part of this paper is why some models worked better than others. They dug into the determinants of performance.
Absolutely. And this is where we get the biggest surprise. In the world of Alzheimer's detection, linguistic features, the actual words and grammar someone uses, tend to be very powerful predictors. But for this broader CI task, the opposite was true. Acoustic features consistently outperformed linguistic ones.
Let's break that down. What do we mean by acoustic versus linguistic features?
Think of it this way. Linguistic features are about what you say. This includes your vocabulary, the complexity of your sentences, how often you repeat words, and so on. Acoustic features are about how you say it. This is often called prosody, the rhythm, the pitch of your voice, how fast you talk, and the length and frequency of your pauses.
And in this study, the how was more important than the what. Why would that be?
The paper offers a couple of great potential explanations. First, since CI is a wide spectrum of conditions, it might not always manifest with the specific language problems, like trouble finding words, that are hallmarks of Alzheimer's. The acoustic patterns, however, might be a more general marker of cognitive load or processing difficulty. Second, the study cohort was diverse, including people who speak English as a second language. For them, English-specific grammar rules might not be a reliable indicator, but the acoustic patterns of their speech could still reveal underlying cognitive changes.
That's a fantastic insight. It suggests that acoustic-based models could be more robust across different languages and cultures. Now, what about the multimodal models, the ones that combine both acoustic and linguistic data?
Generally, the rule of thumb in AI is that more data is better, so combining modalities should improve performance. And for some models, like the one from Ying et al., that was true. The combined model was better than its individual parts. But, and this is a big but, it wasn't always the case.
Oh, where did it fail?
In the model from Farzana et al., the multimodal version performed significantly worse than the version that used only acoustic features. Adding the linguistic information actually harmed its predictive power. It's a powerful reminder that you can't just assume combining data sources will help. Sometimes one data source is just noise that confuses the model.
So the key takeaway seems to be that for general cognitive impairment screening, focusing on the acoustic properties of speech, the prosody, the rhythm, the pauses, is incredibly promising. It might even be more important than analyzing the specific words being used.
Exactly. The study highlights that these interpretable acoustic features, which capture things like affect and prosody, were the strongest performers. While deep learning models like MESA also did well, the success of these more straightforward acoustic features is a really clear and actionable finding.
Of course, they note the main limitation is the small data set, especially the number of people with CI. With more data, these trends could become even clearer.
For sure. But as a starting point, this paper does a fantastic job of mapping out the landscape. It shows that using speech for CI detection is viable, and it points future research in a very specific and exciting direction. Listen to how people are talking, not just what they're saying.
So we're diving into a really interesting paper today called RARL. It tackles a huge problem in medical AI. How do we make these powerful vision language models, or VLMs, actually usable in the real world?
Exactly. We hear about models like MedPalm that are incredible, but they're often trained on massive datasets using clusters of high-end GPUs. That's just not feasible for smaller hospitals or clinics. This paper addresses that head-on, along with two other critical issues: generalization and transparency.
Let's break those down. Generalization is the model's ability to work on new, unseen data. If you train it on X-rays from one hospital, will it work on images from another that uses slightly different equipment? And transparency is the black box problem. We need to know why the AI made a certain diagnosis, not just what it is.
Right? And that's where their solution, RARL, comes in. It stands for Reasoning-Aware Reinforcement Learning. The name itself gives a lot away. They're not just training the model to get the right answer, they're training it to reason its way to the answer.
How do they do that? This is the clever part. They use reinforcement learning, which is basically a training method where you give the model rewards for good behavior. But their reward system is special. It doesn't just give a point for a correct final diagnosis.
Exactly. They designed a multi-part reward function. The model is prompted to first generate its thought process inside special think tags, and then give its final conclusion in answer tags. It gets rewarded for having the right structure, for the accuracy of the final answer, and this is key for the quality and coherence of the reasoning in the think block.
So it's like showing your work in a math problem. You get points for the process, not just the final number. And to make this all work on a budget, they combine this with two other techniques: a lightweight base model, Qwen2VL, and something called LoRa.
LoRa, or low-rank adaptation, is a game changer for efficiency. Instead of retraining all the billions of parameters in a model, LoRa allows you to fine-tune it by training only a very small number of new parameters. This drastically cuts down on the computational power needed. The proof is in the pudding. They did all their training on a single A100 GPU, which is impressive.
Okay, so the method is efficient and focuses on reasoning. How well did it actually work? They ran some fascinating experiments.
They did. First, they tested the approach on a general-purpose visual reasoning benchmark, just to make sure the combination of RL and LoRa was solid. It outperformed standard fine-tuning, especially when data was scarce. This showed the core method was robust.
Then they moved to the medical data, and the results are pretty stark. Compared to standard supervised fine-tuning, their RARL method improved reasoning-focused performance by about 7.8%. But the really big number is in generalization. When they tested it on unseen medical data sets, it performed around 27% better than the standard method.
That 27% is a huge deal. It suggests that by forcing the model to learn how to reason, it's not just memorizing patterns from its training data. It's learning more fundamental clinical logic that it can apply to new situations, which is exactly what you want in a clinical tool.
Another thing I loved was their evaluation method. Instead of just checking if the final answer string matches, they used an LLM as judge, basically using a powerful model like GPT-4o to score both the final answer and the reasoning quality. This led to a really insightful observation.
Yes, the gap between reasoning and final answer scores. They showed an example where the ground truth for a lung X-ray was pneumonia. The model's reasoning was solid. It correctly identified opacities and signs of disease. But its final answer was pneumonia, lung cancer, and other lung diseases. The reasoning was mostly right, but the final answer was too broad. It shows why just looking at the final output is not enough.
And they didn't stop there. They found two more things that gave performance a major boost: prompting diversity during training and reasoning prompting during inference.
Let's define those. Prompting diversity means that during training, they didn't just use one type of question. They used prompts that asked for long explanations, some that asked for short yes-no answers, and some that were open-ended. This makes the model more flexible.
And reasoning prompting is what they do at test time. They give the model a specific instruction like, first, think through the reasoning process step by step, then provide the answer. When they used this prompt, performance jumped significantly compared to when they just asked for the answer directly.
It's like telling the model, okay, time to show your work. And the model, having been trained with the RARL framework, knows exactly how to do that, and performs better as a result. It really underscores that this isn't just about the model architecture, but the entire pipeline, the training strategy, the reward functions, and even how you talk to the model during inference.
So in conclusion, this paper presents a very practical and effective framework. It makes advanced medical VLMs more transparent, better at generalizing, and accessible to institutions without massive computing resources. It's a solid step towards building clinical AI we can actually trust and deploy.
Absolutely. It still has limitations. Like any model, it can hallucinate or struggle with data that's very different from what it's seen. But as a blueprint for building more robust and resource-efficient medical AI, this RARL framework is a significant contribution.
And that brings us to the end of another episode. You know, it's funny, we started today talking about this gap between AI in the lab and AI in the real world, and every single topic we covered really hammered that home.
It really did. It feels like the common thread was all about dealing with reality's messiness. Whether it's a database that you can't just flatten into a text file, or data that's been corrupted, the solutions aren't about having more power, but more cleverness. I loved that idea of using graphs to give an LLM the structural context it was missing.
Exactly, it's about respecting the structure of the problem. And that idea of finding a deeper signal came up again and again. It wasn't just about reading the data, but giving the AI a kind of X-ray vision to see the true shape of a graph, or in the healthcare example, listening for the rhythm and tone of someone's voice, not just the words.
That voice study was fascinating, the how being more important than the what. And that ties so nicely into that final paper on medical diagnostics. It's not enough for the AI to be right. We need it to show its work, to reason in a way we can understand and trust. The fact that they're making that happen on a single GPU is just incredible.
It really is. It feels like we're moving into a new phase. It's less about just making models bigger and more about making them smarter, more robust, and more transparent. It's about building tools that can actually function in a hospital or on a messy business database, not just in a perfect research environment.
A perfect way to put it. It's a really exciting direction, and we can't wait to see what comes next. But for now, that's all the time we have.
Thanks for tuning in to AI by AI. We'll talk to you next time.